Swayam Prabha. Digital India. Educated India.
Let me also sort of make one quick note before I move on to finally tell you the details, the nitty-gritty details of this cake cutting model. Is the fact that note that not only have I given you an algorithm to find a proportional cake division, i.e. a division that satisfies this second set of properties, and not only have I given you an algorithm that's able to find an NV-free cake division, i.e. a cake division that satisfies these first two set of properties. What I have done is also prove that such things always exist. Right, so it's not just an algorithmic result, it's an existential result. I am saying that if you define fairness in one of these two manners, that at least for two agents, I know that not only, I mean, of course, the fact that you can always find them means that these things always exist. Right, so it's a very important point, it's an existential result as well. I'm saying this is like Sanjeevani, it's somewhere there, and not just that, you're capable enough to find it. So this is sort of a constructive proof of existence, sort of a very nice property to have, and we'll see results. In particular, we'll see results for NV freeness with many more agents, where this is sort of a elusive goal, where it's not obvious till now to the entire research community whether even good approximations of NV freeness exist. Well, they exist, but whether they can be computed efficiently. So, in the guise of an algorithm, I have actually also proved that such a fair division in both these senses of fairness always exists. Okay, so having been informal for quite some time, let me actually sort of get to the model. And again, as I said, the cake here is the line segment 0, 1. It's this interval, it's divisible, so you can sort of cut at any point of time. It's heterogeneous in the sense that you have these So now I'm looking at a general case of n agents. So far we have been looking at the very special case of two agents, but now, I mean, you can have a divisible resource, you just don't have two people, you have many people, say you have n players, n participants, n agents. And again, you have valuation functions. So again, I'm assuming here that the valuations are non-negative. So this is the value that sort of agent I has for any interval. A. Right, so again, you have done it for two agents, you have more agents, you can also sort of look at a more general problem. And so that's the setup. These sort of assumptions the first one, which I've already alluded to here, is that the valuations are non-negative. Right, so Vi of I is equal to for all I. So this is genuinely a cake, right? You will not be sorry for having received it. This is certainly by no means a universal phenomena. A very sort of interesting open question is whether existence result hold when these are negative for certain parts, and sort of creatively that's called the burnt cake problem. When we get to sort of open problems, I will sort of detail this a bit more, but this is sort of an assumption which is sort of important to us. Think of it as dividing a good versus dividing a chore, right? So in the chore case, you have negative values. This is something that we'll sort of address later on. For the time being, this is an assumption that we are going to make, that the values are non-negative. It can be 0, there can be part of the cake that you really don't like, it will not be okay, fine, you just, or you don't eat it, you pass it along to me, and that's it. So you don't have negative value for the cake, you're not that calorie conscious, at least I'm not. The second property, the second assumption that we'll make here is that that the valuations are divisible. What does this formally mean? It means that so what I'm writing here is the definition of divisibility. It's a property that I am going to assume on the valuation functions. All the results I'm going to subsequently talk about will work within these assumptions, will work when the valuations satisfy these 3 assumptions, 2 of which are written now. So the fact the valuations are divisible means that for every interval, so let's say, so I take any interval xy and any parameter lambda, so what it says is that, okay, I have some interval xy, this is my interval, and now you give me any scaling parameter lambda, there is going to be a cut, there is going to be a z that's between x and y, such that, and this is sort of for all agents, if agent I looks at this subinterval x to z, then this is of value lambda times agent I's value for the whole interval I. Right. So this in particular means that Abraham can look at, instantiate it for I as 0, 1, the whole resource, the whole cake, and find a point z such that the value is exactly half of the total, the value to the left is exactly half of the total value, right. Now I want it more generally, in particular I want it for all intervals and for all possible lambdas. So pick a lambda, 1/3, 2/3, 0.6, 0.3, pick any interval I. What this says is that you can actually cut it such that the value here, this subinterval, is of value lambda times the sort of value that I has for the entire interval I. Is this clear? Okay, so this, unlike the first property of non-negativity, is an unavoidable assumption. In particular, what this assumption does is it rules out point masses. Right? It rules the fact out that your value is completely concentrated on a single point in the interval. Can someone explain to me why that is the case? So this implies that VI's, the valuation for any agent I, is non-atomic. When I say non-atomic, I mean it's the case that there isn't a single point C where your value completely lies. So when you look at the cake, it's not that there's a specific point and you say, okay, if I get this, I get value. If I don't get it, everything is lost. Why is this? Why does this property, why does this assumption rule this case out? Right. Exactly. Yeah. So it's a perfect example. There's a diamond sitting right in the middle of the cake. Certainly won't want to eat it, but or maybe you do. But there's no way to divide it in the sense that if I look at that diamond, if I give you that point and then I say give me something that's value half of it, you can't break it. So the property gets violated. This means that the valuations are non-atomic. Let me ask another follow-up question. Say if the valuation is atomic, right? Then why does the protocol, or like even for two agents, why am I in trouble? Why is it the case that say I can't find NV-free or proportional division? No? So let's just circle back and say this was the case. Like if there was a specific point in the entire land where there was a diamond, and Abraham's value was just completely concentrated on this diamond, right? And the diamond cannot be divided, cannot be partitioned. Can Abraham then find a point where the value is half and half? Can the first step of the protocol be executed? No, right. So hence, if I have an atomic valuation, if I have the case that the thing is completely concentrated, I am in trouble. The sort of guarantees that I've made informally won't work. So in that sense, this is sort of a crucial assumption. It's an assumption that that's forced upon us. Okay, so that's the second assumption. The third one that I'll make is that the valuations, all the valuations are additive. And this simply means that yeah, there would be no protocol. Yeah, it's a good point. Like it's not just that the suggested protocol would fail. Like there's no way to then divide it into two parts. Like both of the participants, say even in the case of, so here we have like general n agents, but even if I have only two agents, there's a point mass. Both of them only value this, so it's nothing will happen. Like either the first guy will get it or the second guy. There's certainly not going to be proportional or NV free. So point masses are a no-no in this case, and so divisibility is sort of in that sense required. Right. So again, this is second one is sort of essential. The first one can be relaxed. There's some results for like cake division with negative values, burnt cake as it's called. The third one also is something that we'll discuss in the open problem section, whether additivity is an essential requirement or not. But for the time being, this is sort of a natural assumption. It's a standard assumption in this line of work. So we'll sort of, at least for the initial part of things, we'll sort of follow it along. And what this says is that the definition of additivity is quite natural. This says that you pick any two disjoint intervals, I and I prime, and for any agent I, if you look at the value of this union, so this is, note that this union is not necessarily a sort of a single connected piece. This is two crumbs of the cake, two disconnected intervals, but now you can talk about the value that you have, agent I has for this union. This is nothing, again, this is disjoint. It's just the sum of the values. So if you partition it among n pieces, your total sort of value is just the sum of these things. What this lets us do is it enables us to extend the valuation function to finite union of intervals. So that's the formal framework, that's the sort of rules of the interactions that we'll sort of work with. And these finite unions are typically called pieces of the cake or crumbs, so on and so forth. But these are the three assumptions that I'm going to make, and something that sort of follows without loss of generality is normalization. So I'll assume, and again this is just a scaling exercise, there's nothing, it's not a nothing essential about it, that for every agent the value for this entire resource, for this entire cake, is scaled at 1. So every agent looks at the whole cake, the whole segment, the value is just equal to 1, this is normalization. If it's 10, you just divide everything by 10 and you sort of get that. This is sort of nothing profound here. Okay, so 3 assumptions and 1 sort of a normalization property that we can assume. Now with this in hand, if there are questions I can answer them now, or like move on to like circle back to the two notions that we have seen, NV freeness and proportionality, and actually define it more generally. More generally in the sense for like n agents now. Right, so this is sort of teething pains. You'll have to, like, if I want to talk about any formal result, you will have to sort of bear with me for some definitions and basic modeling things. I sort of assure you that interesting ideas will come soon. So far, this is just sort of grunt work in the sense of building towards a common language to talk about this cake cutting problem, like a framework where we can sort of develop ideas and sort of share interesting algorithms and results. But yeah, so it's just so far so good, that kind of the sort of minimal baggage that you have to carry along to talk about these results. And as I said, I'll not be explicit about it, but all the results that we will sort of discuss in the cake cutting context will be under the assumption that these 3 properties hold for the valuation functions. Yeah, again, just be patient and I'll stop with the definitions. But yeah, it's good to have, again, rigor is important. Let's have all the definitions out of the way to like get to nice, interesting results. So first thing, again, this is sort of a repetition, and so I'll define an allocation of as just as an n partition of 0, 1. So n as in there are n agents. I look at my cake, I look at my divisible resource and divide it into disjoint intervals whose union covers the entire cake. So it's a partition of the cake where again the indexing is as before. So interval II is assigned to agent I. So the indexing is, yeah, the subscript always denotes the agent that owns this interval. Right, so this is the definition of an allocation. What is an allocation? Nothing but a division of the cake, a partition of the cake, such that every, an n partition such that every agent gets a unique piece, gets a unique interval. So here's a picture. So say this is the first interval goes to agent 7, this is the second interval goes to agent 3, agent I gets some interval here, so on and so forth. So again, these are all pairwise disjoint and the union covers the whole thing. So you have divided the whole thing. That's an allocation. That's just the solutions that we are after. The output of a fair division exercise in the cake cutting context is such an allocation. So this is what we are after. This is what the protocols are supposed to produce as outputs. For the time being, yes. So the question was, like, are we ignoring the possibility of an agent getting two intervals or like getting two disconnected crumbs? For the time being, yes, but that's also a possibility where you can have you can divide it into many pieces. What's being assigned to an agent is again a union of these intervals. So now you'll not have n partitions, you'll have more than that, and again, but the disjointness sort of holds again. So you partition it into many, give collections of these intervals which are mutually pairwise disjoint to different agents. We'll get to that, but for the time being, let's just, for simplicity, stick to this case. So, okay, finally, right, so after making you jump through hoops, here we go. What's the formal definition of fairness? At least in this context, I'll say that so again, this is, I am writing two definitions into one. The first definition is what does it mean to be proportional, or what does it mean to satisfy proportionality? What does it mean to be fair in this sense? It means that if I look at every agent, I look at the value that the agent I has for the interval that's been assigned to it. Again, recall the subscript convention. So Vi is the value of agent I, Ii is the interval that's assigned to I. This is at least 1 over n. Of course, I'm assuming here that the value has been normalized. So this is 1 over n times 1, the value that agent I has for the whole resource, and n again is the number of agents participating in the cake cutting exercise. So it just says that everyone gets at least a proportional share of the cake. Right. And the second definition, so this holds for all agents, of course. So is this square bracket n notation familiar to everyone? This means 1 through n, right? I have n agents, I have indexed them 1 through n, every agent satisfies this, so everyone is proportional, receives a share that's proportional. Second definition is of NV freeness, and we say that an allocation is NV free if and only if the value that agent I has for its own piece is okay. So what should I write here in this blank space? What goes here? What is that? Ij. Why is it Ij? So what, can someone remind me what NV freeness means? What is that? N minus, so okay, n is not a number, it's a indexing thing. So I mean, it's just like 1 through n here represents like identities. So it just means Abraham, Lot, you, me, Neildhara, so on and so forth. So it says for every person. So if for example, if I look at I am I, my identity is I. So the value I have, like Vi, for the interval I receive in this allocation II is at least, first of all, the first thing notice is that it's Vi, the value I have for what? When will I be NV free? if ij, right? J not equal to I. Why is this? Okay, if I write II here, why is it kind of? It's a good point. Why can't I? Why can I write II here? Exactly. I mean, okay, it's not greater than, it's equal to. I mean, I'll certainly not be envious of myself, right? I mean, I have that peace, I have that peace. It's sort of, there's no existential angst here. I look at my piece and, so okay, I mean, let me write it and then, so this is an important definition. If this is lost, then we are fighting an uphill battle. So let's sort of make sure this is appreciated. I is an index, it's an identity of an individual. So what this says that I look at every individual I. Now I looks at the value it has for the piece that's assigned to it. This is Vi of II, right? The value it's receiving under this allocation, under the allocation that I'm defining to be NV free. This thing right here, and this is said to be NV free if I looks at any other person, looks at you, and then says, okay, you have received ij, but the value I have for my interval is at least as much as the value I have for your interval. So I'll not envy you, I'm satisfied with what I have. In other words, I'll not want to swap with you, right? Certainly, I mean, so it's NV free in that sense. It's a comparative notion of fairness. I am looking at every pair of agents and choose two of them, and now invoking this inequality for every pair. Note that when I instantiate for I, both the left hand side and the right hand side is Vi. Like I is doing this calculation in its own head. I says II is the value I have for me myself. On the right hand side too, it's V of I, the value I have for ij, I'm happy with what I have. So I do not envy anyone else, and this has to hold for every pair of, so it's a comparative notion in that sense. By contrast, the first definition, proportionality, is a threshold based notion, where you are saying, okay, I look at what I have, I look within, in the sense I just look at the piece, and the value I have for that piece is at least proportional, it's at least 1 over n the value I have for the total resource, right? So that's a threshold based notion of fairness, it's a comparative notion. Think back on the cut and choose thing for Abraham and Lot. We had sort of, we had both of these properties for the n equal to 2 case. I will not go through it again. It's a useful exercise for you to actually go back, look at the cut and choose protocol, work with the assumptions and the valuations we have outlined, and convince yourself of the fact that this property indeed holds for the n equal to 2 case for the case of 2 agents. And this is a good point for me to stop, we'll sort of see how easy and hard these sort of definitions are. But let me ask this question again. For general n, which one do you think is easier, which one do you think is harder? Or they are kind of incomparable, always the same, don't care, looking late for coffee. Two implies one, that's perfectly right, yeah. Perfect. Exactly. So after the coffee break, we'll see why, with the 3 assumptions that we have made on the valuations, why 2 implies 1, why 2 in that sense is a stronger notion of fairness than 1, and like hopefully by the end of the day you'll appreciate that 2 is really elusive, and in contrast 1 can be achieved sort of is a much more palatable, it's a computationally much more tractable solution concept. It's a notion of fairness that can be achieved much more generally. So that's sort of the agenda for the next lecture. But yeah, again, it's probably a good time to stop, and we'll sort of reconvene after the coffee break. All right, thank you.